Mini series about mechanical design engineering interview questions, and pretty much we are going to discuss about our technical questions. This interview will be presented by, or we will go alongside Mr. Samuel. As you can see, this is an empty room because it's a pandemic, so interviews are going to be held remotely. And it's 2 o'clock. As I told you, it's an interview time. The only thing or the only person who is missing is Mr. Samuel. Let's find him. Looks like he's running and he's on time. He's pretty pumped up also. Let's see if that kind of energy is good for interview or not. Interviewer who possibly can become the future boss of Mr. Samuel. Uh, he's got the first question is throwing is the doorknob question. I want to highlight that there are several versions of it. The only thing to take away from this particular question is how normally interviewer frame questions. In this particular case, what he's saying that there is a doorknob and this particular doorknob design is failing at their customer location. When the company further inquired why it's failing, they figured out or they found that children like to hang on the doorknobs, and some people used to like hang on their groceries and other stuff to this doorknob. It's quite common. And but this particular doorknob is not able to take that load and it's failing. Having this information, our interviewer has asked Mr. Samuel, how will you improve the doorknob design? Uh, Looks like Mr. Samuel is very confused. He's thinking that all the courses which he took during his college days and all, does it even relate this problem? Does it even relate to that kind of stuff? In all such scenarios, one thing everybody should know is before even answering or thinking about it, draw it. So first thing which needs to be done as a mechanical design engineer is draw whatever is coming in your mind, draw the problems which are being given to you. Uh, the first thing is there should be a door. So we have made a door, and then there needs to be a knob. Oh, we forgot about the kid. So there is a kid and he is hanging onto the door. What it does, it kinds of give you a boundary conditions which are very important when we will like figure out how to solve it. Once now you can see, right, like this is our overall problem. The next item which we need to do is convert this problem statement into a free body diagram so we know where are all the forces and stress. Let's do it. So the door, we have finally figured out that the knob is connected to the door and we have called it like a fixed location. And we have removed the kit but put a force instead of a kit, and that force will resemble a kit or a grocery bag. Let's further refine into it. Uh, so we replace the door with a fixed support because now we are saying that particular interface is fixed, and we simplify the doorknob with a beam, a rectangular beam to be precise. Uh, the force by the kit or the grocery bag is now termed as F2. One thing which we always misses out is everything which we see has some sort of mass. So the doorknob also has a mass that will be represented by a force F1. And when you have two force facing downward, we will have a reaction force facing upwards. Uh, it's not shown here, but yeah, you can make a moment diagram where moment will be following the direction of force. Looks like Samuel is happy. Now he thinks that he figured out the problem. Apparently, yes. Uh, it looks like it's a cantilever beam problem. Uh, so now we have force F1 and F2 acting on a cantilever beam of length L, having a breadth of B and a height of H. Uh, as an engineer, we always have to make assumptions. We are not supposed to like dive into problems having all sort of forces acting on it. We should first try to simplify it. So the first assumption here we are making is uh, the kit weight is way higher than the weight of the doorknob, which makes sense, right? Doorknobs are like few grams, or 50 gram, 100 gram, at max like 150 grams. But kits usually are like 5 kgs to 15 kgs. It depends, right? So it's fair to assume that the doorknob is way less than the kit. So we can pretty much get rid of this force due to its own weight. Uh, then now our problem, we can refine it, and it now converts into deflection. That when a kid hangs on to it, this particular beam is bending and it is deflecting. And it's very intuitive also. If you think about it, the deflection here, it says that it's depend upon the product of force into L cube, that's the length. If we think about it, the more force we apply means if a heavier kid or a kid having a bigger kid just hangs onto doorknob, it is going to bend it more, right? Uh, the length, if I make the doorknob longer, it is going to bend more. But what this formula tells us is that uh, if I change the length of the doorknob, it has a cubic uh, relation to the deflection, which means that it will have a more impact. The denominator is a product of elastic modulus and moment of inertia. Elastic modulus is a material property. We are going to discuss some more about it in part 2. Moment of inertia, it's again uh, depends upon a design engineer what kind of design he made, and that will define the moment of inertia. Let's see what Samuel's come up with. So he figured out this problem is about minimizing the deflection. And as we spoke about, length is something which we can change, and it will have more impact than any other factor because it has a cubic relation. Means if I decrease the length by say half, my deflection is going to be reduced by 8 times. So he says, let's reduce the length, and based on the same logic. Looks like Samuel is buzzed. He's like, oh, I figured it all out. Let's see what the interviewer has to say. What interviewer is saying is, oh, apparently you cannot change the length because the packaging in which those doorknobs come, they have ordered like so many cases and they are all being booked for like 1 year. Uh, so he's asking Samuel, what are you going to do next? Samuel is thinking like, really, packaging is the constraint. But since this situation the interviewer has given to Samuel, he has to think about it. So let's go back. Let's again look at deflection. Deflection is again a product of force into L cube. And then in the denominator, we have modulus of elasticity and moment of inertia. Let's learn more about moment of inertia. In this particular case, since it's a rectangular beam, it's by product of breadth into height. And in this case, height has a cubic relation, which again highlights that if I have to decrease the deflection, what I need to do is increase the height. It is a factor where I just increase it by 2 times, my deflection is going to be decreased exponentially. So Samuel is saying is please increase the height. Probably this is the second best option alongside increasing the length. He's very about, but let's see. Boss is saying that when I said you there's particular box in which this doorknob come, we cannot change it. So I'm saying you cannot change the length, you cannot change the height. Looks like uh, Samuel has to dig some more. In the next part, we are going to discuss about it. What are the other options which design engineer can take in terms of material selection? Uh, so for this part, before saying goodbye, there are a few other questions, follow-up questions. Sometime it will do ask, so I just want to list them down so you have like some idea about it. The first being when I said that this whole thing is going to go under bending stress. Is there a particular location which does not see this bending stress? In fact, yes. Let's see. So when we have this cantilever beam, we always have a tension and a compression. And this tension and compression, compressive force, uh, they are divided by a neutral axis, or I would say a neutral plane. In that particular neutral axis or neutral plane, we don't have any bending stress. Maximum bending stress uh, is this whole beam or whole doorknob. Does it face same amount of bending stress? No. Uh, as you can see in the picture, the neutral axis has zero bending stress. As I move up or down, the bending stress increase or decrease. If I go up, in this particular case, it will go under tension and the bottom half is going to go under compression. At the same time, we should know that this moment, it depends upon the product of force into length. So the maximum moment will be at the interface where this cantilever beam is starting. So the maximum bending stress will be at location either at the top or the bottom, right at the junction of this cantilever to this fixed support. Uh, is there a shear stress? Yes, because as you can see, right, this force, how this force is acting, it will induce shear stress, and the magnitude will be equal to F, because this force is almost at the very edge of this uh, cantilever beam. Do we need to consider all the stresses? Uh, and the simple answer is yes. And we are going to discuss this because whatever we design, we have to design it with the intent of having a factor of safety. That is something this particular design engineer missed out. So we are going to discuss more about the approaches in coming part 2 and part 3. For this video, that's the end.